Okay. Recording for Friday's class, March 20th. And by the way, if anybody's out there going, ew, he's still wearing the same shirt he had on Wednesday. Actually, it's Tuesday. And I just finished making the other recording like 10 minutes ago. So everything's okay. Anyhow, I got a little bit of section 9 started in the previous class. There's still the tail end of it right there. I introduced Faraday's law of induction. I'm going to go on talking about that today. As for what I'm trying to do is I'm trying to follow the original schedule that I gave you on the syllabus the first day of the semester. And for Friday, it says what we're supposed to do is, I've got it right here. Yeah, for Friday the 20th, start section 9. Well, I'm just about 10 minutes ahead of schedule on that, 10 or 15 minutes. And then, so I'll continue through section 9 today. For Monday, it says quiz 8. Well, that has to be postponed because we're not going to see each other on Monday, but the rest of the period was supposed to be the review. You'll have to work on that on your own. But let me remind you that solutions to those reviews for the exam, I mean, yeah, I've got solutions all printed up for you in my office, but that involves actually, you know what I should do? I should try and remember to give them to you. Hopefully I'll be seeing you when the real Friday gets here, and I should remember to pass those out. But if I forget or you don't pick one up or whatever, remember it's available on the website. There's a thing you can click on that says review solutions, and you can go down in there. So that's what's scheduled for Monday, the 23rd. The next time I was planning to do a lecture was Wednesday, the 25th. So that'll be the date that goes with the next recording that I do after this one. Maybe I'll have a different shirt on by then, we'll see. And let me remind you of the actual, assuming that we manage to continue meeting on Tuesdays, this is changing constantly, and for all I know by then, did I say Tuesdays? Assuming we manage to meet on Fridays, this Friday the 20th, I'll have quiz number 7 for you, because that was supposed to be the Monday immediately after break. But after that, we're going to have to start doubling up in order to fit everything in the limited number of times we're going to meet. So Friday the 27th, both quiz 8 and exam 2 on the same day. Fun never ends. And so keep in mind that that's what's coming up. Okay, Faraday's law. You have a loop of wire, and for one reason or another, the magnetic flux through that loop is changing. This could happen in several different ways. The example that I started out with was something like a generator where the loop of wire is spinning around. Flux, well, I erased that part, but flux is BA cosine of theta. In a generator, it's theta that changes as the loop constantly changes its orientation while it's spinning around. In this first example that I'll do in a few moments here, 9-1, it's B that changes. You've got, in case you haven't picked up the handout yet, can I get that to, there, it's in focus. Quick, pause it right there and look at it. As the bar magnet gets closer and closer to that loop of wire, the magnetic field at the wire's location is getting stronger and stronger, and that's why the flux is changing in that case. So with the generator, changing theta changes the flux, and in this case, a changing B is the reason the flux is changing. And before the unit is over with, I think I'll even have one example where it's the area that's changing, and that's why you've got a changing flux, unless that's in the next section. But I know I've got one of those somewhere in the course. So in this one here, the magnetic field changes steadily. So therefore, I should probably point this back over here. You do not need to resort to infinitesimals when things are changing at a steady rate. It's just like back at the beginning of Physics 131, when we did velocity and acceleration. Acceleration is the derivative of the velocity with respect to time, but if something is picking up speed at a steady rate, there is no need to chop it up into infinitesimals. You can just say delta V over delta T. The same thing here. Because it's changing at a steady rate, we can just say delta phi over delta T. And so that's what I'm about to do. Since it's just a single loop of wire, n equals 1. And the reason that it's delta rather than d, once more, is because the flux steadily increases. Flux is BA cosine of theta. In this case, the cosine factor is equal to 1 because the area vector is along the axis of the loop. And the maybe I should draw a little sketch. There's a place where there's a little, I'll stick it down here for a moment. Okay, you've got, well, the area vector would be either that way or that way, depending on which way the current goes around the loop. We'll see how to figure that out in another week when I get to Lenz's law. But for now, maybe it points that way. It's along the axis anyhow. If you've got, is that the north end? Yeah. If you've got a bar magnet, the field lines come out. So that's the area, that's the B vector. And the point is that B and A are pretty much parallel. I mean, yeah, the field is somewhat non-uniform. The field lines kind of spray off to the sides somewhat, but basically B and A are in the same direction. So you've got the cosine of 0 degrees, which is 1. And so the flux is just B times A. So B times A final minus B times A initial, delta phi. But the magnetic field starts at 0. It says increases from 0. So apparently it starts out with the magnet really far away. And so initially B is 0, and that wipes this part of it out. So incidentally, the significance of the minus sign, well, that's something I'll explain before everything is said and done, but for now, we're not too concerned about that. Don't start pulling your hair over the minus sign. I guess and I'll say this again before the course is over, this is just a convention, okay? You don't have to have the minus sign. If your EMF is a voltage, and you've done enough labs at this point where you're familiar with how to use a voltmeter, you've got two wires coming out of the voltmeter, and maybe there's a resistor, for example, there on the circuit that you've constructed. If you put the wires on either side of the resistor the one way, you get a positive voltage. If you switch the wires so it's the other way around, now you get a negative voltage. So is the voltage positive or is it negative? Well, that's kind of your choice when you're standing there hooking up the wires. So it's kind of just a convention that makes this negative. It has to do with which way the current flows around the loop, but enough said about that at this point. B, final, is 0.002 of a Tesla. A for area. It's a circular loop of wire. I mean, it kind of looks sort of like an oval because the idea is you're looking at it from an angle, but the radius is labeled there. Ovals don't have a radius. They have a major and minor axis. That's supposed to be a circular loop of wire. And the area enclosed within a circle is pi r squared. And it says that the change occurs over 2 seconds. That would be delta t. So you run all that through your calculator. Negative 2.83. It's not a lot of voltage. Nobody's going to get electrocuted by that. 2.83 times 10 to the negative 6. Well, first of all, it's not a particularly strong magnetic field. It doesn't change particularly quickly at all. And it's only a single loop of wire. You know, if you had 1,000 loop of wires, if N was 1,000 instead of 1, well, that would at least get you up into the millivolts instead of the microvolts. But a variation on the same principle is able to produce thousands of volts in those great big generators. Of course, you know, you get a great big industrial sized generator, there's a much larger area enclosed within the loops of wire also. That helps boost the voltage quite a bit. Number 2 is a follow-up question on the same situation. If the loop has 5 times 10 to the negative 4 ohms, how much current flows? Well, once you know the induced voltage, getting the current is just Ohm's law, okay? So according to our friend Mr. Ohm, Herr Ohm actually, I suppose, I equals V over R. 0.83. Times 10 to the negative 6 for the voltage. The resistance that was given in the question for R. Assuming it's just a loop of copper wire, it wouldn't have a lot of resistance. .66 milliamps. Flowing around that loop with no visible source of voltage, and that's why it's called an induced current. Applications. Well, one application of induction is generators, which is kind of important important for our modern way of life. Another important device that uses induced voltage is a transformer. A transformer is a device used for changing voltages, okay? After the electricity leaves the generating station, they step the voltage up for long distance transmission. Before it comes in your house, they bring it back down a couple steps at a time, because, you know, if they brought 300,000 volts into people's houses, they would probably kill all their customers the first night, and that's bad for business. And then, well, anyhow, the device used to change voltages when you step it up and step it down like this, or inside your cell phone charger where they have to step it down to a voltage that's appropriate for charging your battery. That's all done with transformers. A transformer, like it says there, I'm always moving this the wrong way and holding it too close. Got it. A transformer is a pair of coils arranged so that the same magnetic flux goes through both. The changing current in the primary coil creates a changing magnetic field. This changing magnetic field also passes through the secondary coil, where, according to Faraday's law, it'll induce a voltage. So in this next example I'm about to do, the solenoid is the primary coil. It's supposed to look like it's been plugged into a regular household outlet. And I've written the function there that describes how the voltage changes with time, which would actually be fairly realistic. That has the correct frequency to be ordinary household alternating current. And the short coil that's wound around the long one would be the secondary coil. All of the flux passing through the primary coil also passes through the secondary coil because the primary coil itself passes through the secondary coil. And so the changing flux passing through that second coil will induce a voltage in it. And that's not the only geometry that can be, probably not even the most common geometry as far as how a transformer is constructed, but that's the idea. So the question is the induced EMF in that short coil as a function of time. Time to move the camera. Short summary of how I'm going to approach this. What's the plan of attack? Well, the primary coil is a solenoid, and we have a formula for the magnetic field in the solenoid. So from the formula for I as a function of t, I can get B inside the solenoid as a function of t. Times the cross-sectional area, now I've got flux as a function of time. Take the derivative of that. This time I can't say delta phi over delta t because it's not changing at a steady rate, it's changing like a sine wave. So you got to take the derivative, put it in Faraday's law, and that'll give us the induced EMF. Details like this. Inside the solenoid, magnetic field in a solenoid from, I guess, a couple of weeks ago. At this point, it was one of the examples well, I guess that was back in section 8 where I first came up with that. This was one of the special cases that I did as an example of Ampere's law. Fill stuff in. Mu naught 4 pi 10 to the negative 7. For I, the current, I have a function rather than a number because it's an alternating current. It's constantly changing. So you don't have a number, you've got a function of time. 20 cosine 377t. And this is the magnetic field of the solenoid I'm calculating. So we want the number of turns in the solenoid, which is the 500. And the length of the solenoid is on the picture somewhere, I think. 0.10 of a meter. Yeah, it says 10 centimeters length there. So you push a lot of buttons on your calculator. And if I fill in all the units, like I don't actually usually bother to do, of course, there's a whole glob of units on mu naught, and then the 20 would be in amps, the 500 is dimensionless, we got meters on that, and what you're left with is Teslas. The magnetic field is measured in Teslas. A Tesla is equivalent to a Weber per square meter, which is kind of a handy way to think of it for what comes next. And we've got the cosine of the, and actually I didn't bother to write the units on the 377, but that's in radians per second. So if it comes to where we have to punch something up, which actually no, we don't. But if you did have to punch something up on your calculator, you'd want it to remember to have it in radian mode. So that's the strength of the field. Now, next question. How much of that field stuff, how much flux passes through the interior of the solenoid? Well, that would be B times A. Flux is B times A. The usual point for confusion here, people see the A for area and they go, oh yeah, okay, I'll look up the formula for the area of a cylinder. We've got a cylindrical coil here. Surface area of a cylinder is, I should mention right in the middle of this, make sure there's no mistake, this is how to do it wrong, okay? People look at surface area of a cylinder, 2 pi r times the length, and no. A is the cross-sectional area of the coil, not the lateral surface area of it. Remember, we started out talking about single loops of wire, and the area enclosed within that loop is the A in B times A. Well, now, when we extend that to a coil that's a whole lot of loops of wire instead of one, A is still the area bounded by each loop of wire, okay? So cross-sectional area of the coil, not its surface area. In other words, what is the area? What is the area that all those lines of flux pass through? Okay, that would be the cross-section. So the flux through the primary then, magnetic flux. The theta in BA cosine theta is 0 degrees because the area vector points, the area vector for each loop of the coil points along the coil's axis, and the magnetic field of a solenoid also points along the coil's axis. So B and A are parallel, and you've got the cosine of 0 degrees, which is equal to 1. And So we've got the expression for B that I have written above it. That goes in for B. 1 centimeter radius, 0.01 of a meter, pi r squared is the cross-sectional area. And so you put all that together and the flux is 3.96. Webers per square meter times square meters gives you flux in Webers. Okay, so that's the flux through the primary coil. But assuming that the field outside the solenoid is weak enough to ignore, this would also be the flux passing through the secondary. In a well-designed transformer, both coils are linked by the same flux. So this is also the flux through the secondary coil. So the EMF induced in the secondary coil is given by Faraday's law. That secondary coil has, the short one, has 2,000. Oops. As for the derivative of the flux, well, the coefficient there, 3.9 times 10 to the negative fifth, that's just a constant. The way you take a derivative, of course, is you just sort of recopy any constants, any constant coefficients. So 3.96 times 10 to the negative fifth. The part that you have to take the derivative of is the cosine of 377t. Now, the derivative of cosine is negative sine, but this isn't just the cosine of t, it's the cosine of some more complicated expression involving t. So it's a function of a function. You have to use the chain rule, okay? So the way I always think of the chain rule is it's the derivative of what's outside the parentheses times the derivative of what's inside the parentheses. The derivative of what's inside the parentheses would be 377 times t to the 0 power. So the derivative of what's outside the parentheses, derivative of cosine is negative sine. times the derivative of what's inside the parentheses. The derivative of 377t is 377. So the thing kicks out a factor of 377 because of the chain rule. And to simplify, well, actually, before I multiply it by everything else, I just want to sort of notice in passing what just the d phi dt part of it is, because I'm going to use it again in a later example. So make some mark in the margin of your notes or something to make it easy to refer back to that sometime, probably late next week, so that you can find that again when I get to example number 5. But for right now, to finish this one off, I need to multiply that by 2,000. The minus signs will cancel each other, and the EMF induced in the secondary coil is that times 2,000 gives you just under 30. So you put an alternating current into the primary coil, and an alternating voltage is induced in the secondary coil, from which, you know, if you hooked it up to some device, you could have an alternating current flow out of there. We've got an amplitude just under 30 volts. That is determined, among other things. We'll get back to this. Actually, I don't think it's till unit 12, but at some point, I'll get around to pointing out that the ratio of the voltages is the same as the ratio of the number of loops. Okay, the number of loops in the secondary coil went into the soup at that point there, and the number of loops in the primary coil got included back here at the beginning for the, you know, the mu naught IN over L. And so when you work through the details, it turns out that if you've got, for example, a 5-to-1 ratio between the number of loops, there'll be a 5-to-1 ratio between the voltages under ideal conditions. But let's move along. Number 4. If I can manage to turn the page. There we go. To rephrase the question a little bit, you know, what if I had put a direct current into this solenoid instead of an alternating current? What would we have for an induced EMF then? The answer is 0. Okay. Transformers do not work on steady direct current because a time derivative means a rate of change. If you have a steady DC current in the primary coil, it will produce a steady, unchanging magnetic field. The times the area gives you the flux. The flux here would just be a number. It wouldn't be a function of time. It would just be a constant. And when you take the derivative of a constant, you get nothing. Induction works on change. the more rapidly the flux changes, the bigger the induced voltage. If the flux never changes, nothing gets induced. So explain why transformers don't work on steady DC. Kind of summarize that. I guess it's time to slide my camera over again. Faraday's law. EMF equals number of loops times, well, never mind making it look like some kind of formula. As far as what it means in words, the rate of change of the flux, to be precise. And if you have just a steady current in the primary, nothing is changing, so nothing gets induced. And then I put in parentheses something about how this device is the main reason the power company makes alternating current, not direct current. Actually, the first electric power company in the United States sold direct current. Okay, Thomas Edison started a company, I believe was in the middle of Manhattan somewhere. And Edison was all about direct current, as some of you may already know. You can get away with that in a high population density area. Middle of Manhattan, he had lots of customers within just a very few miles of his generating plant. The problem is when you start trying to send electricity longer distances. And the problem is energy lost along the wires, okay? If you're going, there is electricity, there's a lot of hydropower up in Quebec. And I think maybe in the 1970s, was it? They built a transmission line from there all the way down into New York City, hundreds and hundreds of miles, okay? So if you want to do something like that, the problem is anytime you send an electric current through a resistor, heat is generated at a rate equal to I squared times R. This includes the power lines themselves. I mean, they're big fat wires, so it's just a tiny fraction of an ohm per foot. But there's a lot of feet between Quebec and New York City, okay? And it adds up to a significant amount of resistance. And, you know, if you're in the business of, if you're an electric utility, you make money by selling energy to your customers, not by heating up the outdoors. And so you want as little energy as possible lost along the lines. You want the energy to get to the other end of the wire where you can sell it to people. And that means minimizing the amps, okay? So I squared R losses to heat are the problems. Now, power is equal to I times V, but this time I'm not talking about the power lost along the line. I'm talking about the power that makes it to the other end. How many watts are going to be there to give to your customers? And notice there's a trade-off, okay? You can have a lot of amps and not very many volts. This is what's done in a car, for example. A car is a 12-volt system. The starter motor needs a significant amount of power to turn the engine over, but it's only a 12-volt system. So you got to have something like 100 amps to deliver enough power to crank this thing over. That's why if you open up the hood of a car, the cable coming off of the battery is about as big around as your pinky finger, because you need such a big fat wire to handle all that current. So you can have lots of amps and not very many volts. Well, that's fine under the hood of a car where the stuff's going to go 3 feet before it gets to the starter. But if you're trying to send electricity from Quebec to New York City, it's the amps that heats up the lines, okay? So you want the volts as high as possible to make the amps as low as possible so that you can minimize the I squared R heating along the lines. So the generators create a voltage that's somewhat higher than what you have in your house. I don't know exactly right to the volt. It's a few thousand volts, 5,000 volts, something in that neighborhood, I think. But as soon as it leaves the generators, you have these great big transformers. And the reason I keep mentioning that one particular line that comes out of Quebec is because it's the highest voltage I'm aware of. That one runs at 760,000, I think it's 760,000 volts. That's over 750,000 volts. So that they, you know, for the reasons I just mentioned. Well, then you get to the other end of the wire. You have to bring it down. There's a substation that brings it down to the voltages that they run along the side of the road, which is a few thousand volts. Again, I don't remember exactly. It's like 5,000 volts or something in that neighborhood. There's a transformer on the pole out in front of your house, sort of a cylindrical thing. Quite often there's cooling fins on it. That steps it down to the 120 volts that you have inside your house. And then, you know, there's a transformer in your cell phone charger to step it down to the voltage of the battery. So I just got done saying how transformers don't actually work on steady DC, whereas with an alternating current, it's kind of a natural thing that it works real nice. So even though Mr. Edison hated direct current, and the only way that General Electric was able to get deeply involved in AC equipment was they eventually, as I understand the story anyhow, they eventually had to force out the guy who founded the company. They had to get rid of Edison because Westinghouse was going to kill him otherwise. Because Westinghouse, you know, George Westinghouse, he had Nikolai Tesla working for him, and he had all this AC equipment. And especially with the technology of the late 1800s, early 1900s, it was so much easier to change voltages with AC than it was with DC. And that's why your house current is an alternating current. So what I wrote here is, this device is the main reason the power company makes AC, not DC. For long distance power transmission, low current reduces the losses to heat. Yeah, I said all of that already. One thing I always throw on the end is, usually I ask for a show of hands. Does anybody know how they do this in a car? Because the ignition coil in the car is basically a type of transformer. Everything in a car is 12 volts DC, the lights, the heater fan, the sound system, except for the spark plugs. You need thousands and thousands of volts to throw an arc across the gap in the spark plugs. So the ignition coil steps the voltage up, but cars are DC, so how do they do that? And just like every other time I ask this question, no hands go up, although in this case, that's because there isn't anybody in the room. I'm standing here talking to myself like some kind of lunatic. But the answer is, they turn it off and on, okay? Now, if you had an old enough car, and I'm talking seriously old at this point, they got rid of the points. Let's see, I once had a 73 that still had points. And I once had a 75 that had gone to the electronic ignition. So that's the time frame we're talking about. But you know, if you're cruising around in your 68 Chevy Nova, you know, you pull off the distributor and you look down in there, and there's what amounts to a little switch, okay? Just contact points, just, you know, two pieces of metal that there's a cam that makes them open and close and open, close and open, close and open, close and open. And the reason they got rid of them is they were a maintenance item. After 15,000 miles or so, they'd get all scarred up, you know, they'd be all charred and pitted. And it's like changing your oil. Every so often, you had to change the points, plugs, and condenser. Condenser is an old-fashioned word for a capacitor. And but what that did it was the current to the primary windings in the ignition coil. Turn it on, turn it off, turn it on, turn it off, turn it on, turn it off, over and over and over again. Every time you turn it on, the magnetic field builds up. Every time you turn it off, the magnetic field collapses. Every time you turn it on, the magnetic field comes back. There's your changing flux that will induce a voltage for you, okay? So you can make a transformer work on DC, but you have to chop it. On, off, on, off, on, off. Steady DC transformers don't work. Anyhow, a little bit of technological background. Let's look at Faraday's law on a more fundamental level, is what this says. Well, you know, actually, this, I think it's a little bit less than the full 55 minutes, but you know, the nice thing about doing this on video is if I want to make one recording a little on the short side, a little on, next one a little on the long side, I don't think that matters too much. So since we're kind of between topics, maybe this is a good place to leave off for today. Hopefully I'll see you on Friday.